I've just given you a huge heap of papers, including lab report, quiz, the in-class exercise we did, 3 sets of lecture notes, maybe some other stuff, I don't remember. What I hope that you really get, though, is those 3 sets of lecture notes. It's including today's class period and then next week. We won't be having a physical meeting next week on Tuesday and Thursday. Let's go through these announcements. Right now, the lab that you're on is developing a lab experiment. You're supposed to design the experiment. So I've identified something that I want to know. I want to know the roughness coefficient for stainless steel. And you have to design the experiment that should be used to characterize the roughness coefficient for stainless steel. And then later on, when you execute that experiment, you're going to compare the values that you experimentally derive with published roughness coefficients that you find online for stainless steel. There's a website called Engineering Toolbox. I think some of you have probably already seen that website before, but they have some published values for stainless steel C values. So that's what you're doing right now in lab. And remember that you need to upload the handout you develop by 2 p.m. on Tuesday the 11th. Now, we won't have a class meeting at all next week, and we also won't be meeting for lab. And the reason for not having a lab meeting, besides the fact that I won't be here, is that you're supposed to run that lab independently. You're going to conduct the experiment you design on your own anytime next week between Monday and Friday. The equipment will be available through 5 p.m. on Friday of next week. So that's where things stand with lab. I've got your assignments 5B just now. The assignment that you need to submit next Thursday, we're going to handle the same way we did the assignment that you submitted last Thursday. Last Thursday we also didn't have class. You put the assignment into a folder that was in the excuse me, it was in the box beside my door. The grader took that folder away at, what did I say, 11 o'clock is when he took that and started grading them. So you need to submit your assignment homework 6A by 11 a.m. on Thursday, November 11th. The grader has the solution. We'll start grading the assignment as soon as he collects that. So, any questions about these announcements? The lectures are already posted on MU Online. Class 23 and 24 are already posted online. Those include pencasts, which is when I would have been doing a whiteboard example. Instead, I create a PDF where you actually see my chicken scratch handwriting and I do the calculations. But those have been edited into the YouTube video that's posted for lecture 23 and 24. So you should have everything you need to go through those. The only piece that's missing is office hours. Since I won't be around next week, I can't hold office hours. And what I'll do is pay special attention to my email while I'm gone, so that if you have a question you can't figure out on the homework assignment, send me an email and I'll take the solution manual with me so that I can take a look at what your question is and do my best to respond. Yeah. It's the Thursday before Thanksgiving. Yeah. Right. That's a good question. So asking about whether the tests are cumulative. It would be impossible to write a non-cumulative test because all of the concepts in chapters 4, 5, and 6 are built on like principles of density and fluid properties. And so I won't give you a question that comes only from those chapters, but because our material is naturally cumulative, you kind of still have to know the things from chapter 2 and 3. So I would suggest no, don't like go back through the homework assignments from the first part of the class and resolve those. But as long as you know those concepts well enough to do the questions from 4, 5, and 6, then you'll be all right. Brandon? That's right, Thursday the 18th. Oh, is it a Tuesday? Yeah, I don't have the schedule in front of me. Let's just double check. Oh, during the lab time, of course, that's right. Yeah, so let's see. Thursday the 18th, or Tuesday the 18th. Yeah, right. Okay, so yeah, we're doing the flip-flop again. And now that you bring it up, I'm glad you mentioned that. I remember that the announcements that I have for class 23 and 24, if you look at the handouts, I think I do say some stuff about the tests there. Yeah, so if you look at the handout for class 24, I say the midterm exam is Tuesday at 2 p.m. You can prepare a one-page equation sheet. The coverage is 4, 5, and 6. So I do hit on the upcoming midterm exam when I get to those announcements in the recorded lectures. Yeah. So we'll do that day's lab during our lecture time. That day's lab is another chance to get exposure to Water Gems, which is that software program that Bentley makes. We'll do a little bit of Water Gem stuff during our 75-minute lecture period, and then having the exam at 2 p.m. will give you more time to solve it than you normally would during a normal lecture. I'll ask the grader to put them in my box, yeah, so that you can have access to them. Right. But it's not certain that it's not, you know, I don't know if these assignments will be submitted in time for the back to you in time for the exam. So if you want to, you know, study the assignments that you're turning in, like the chapter 6 ones, you may want to make a photocopy of those before you turn them in, because I don't know if the grader would be able to grade it and get it back to you soon enough for the test. Other questions related to schedule issues? Okay, we're getting into chapter 6 now, which is the momentum principles that were covered during the lab that we had, not this past Tuesday, but the one before, when we were doing the deflector plates. We're going to talk about some of the principles related to that, and to start it off, we're going to watch a video about somebody who made an interesting contraption, a dangerous, interesting contraption.
Ei ihan kevyt olekaan. 3 kiloa kappale painaa kenkä. Siinä on kaikki polttoaine tulee valmiiksi.
Oletko kokeillut lenkillä? Lisääkö juoksutehoa?
Ei no.
Tuolta siis niinku hönkää vai?
Lisa?
No.
What are you gonna do with us?
Fly. I like flying.
That's kerosene in the bottle. Kind of expected to explode that way, right?
It's here.
That's kerosene that he's strapping into his little wingsuit.
Love the helmet. Hyvä. Meillä toi.
This is Finland. Very rough country.
No.
I just said that this kind of weather, if you land on the water, you're gonna die.
Rubber track. Tuutte jäille. Nani?
Hey! I was fucking first one to do it. I jumped from 2,200 meters and flight until the gas tanks were empty and all pulled 1.5, and I was able to maintain the flight level in 2,000 like a half a minute.
All right. Looks pretty fun, right? I don't know that I'd do that necessarily, but it seems exciting. Normally, when you've got a wingsuit, the best you can do is for every 3 feet you fall, you can get 1 foot of horizontal movement. You know, those wingsuits are not perfect wings at all. It's just sort of a way of deflecting some of the air so you get a glide ratio that makes it feel like you're flying. I think some of the real pros, if you watch videos like this on YouTube, you can see them jumping very close to mountains in France. There's some mountain in France that it's just the right slope, this mountain, so that when they're going down it, it sort of feels like they're flying over the level surface. It's just that they're falling at the same slope as the mountain itself. But with the jet boots, he was able to achieve thrust that he maintained a horizontal flight for just 30 seconds. He said half a minute. He was at 2,000 meters for half a minute. I've looked and looked for additional videos since then, and I can't find anything, which makes me think maybe things went poorly one day. I don't know. It seems like that's an awesome thing, right? They should have lots of high-resolution videos and music in the background, but I haven't been able to follow up on that guy. I did get some specifications, though. That, you know, the one flight that I did find that you've just seen, I found some information about like what's the burn rate, what sort of thrust is in those jet boots, and so on. And each boot gives 16 kilograms of thrust. Now, thrust or force we usually express in terms of newtons, and so if it's expressed in terms of a mass like this, all we have to do is multiply that by g, and it converts it into how many newtons of thrust it is. To get the jet primed and warmed up, it started off with a mix of butane and propane, and then once it's warmed up and spinning, then they switched over to jet fuel, which is essentially highly refined kerosene. And the reason why he was only able to fly for about half a minute is that the burn rate of the boots, it's going through half a liter per minute on each of the boots. And so you noticed, you saw him strapping those bladders of fuel in. It looked like maybe he had a liter each. But of course, the boots are running before he jumps, and so he probably burned through half of his fuel just getting situated on the hot air balloon before he jumped off. It's equivalent to 7,000 feet where he jumped off, and then he tried to climb to gain altitude, but the wingsuit's just really not developed for something like that. And in the write-up description I found online, when he tried to gain altitude, then it would stall, but he did achieve horizontal flight for a little while. So we're going to refer back to this idea of the jet boots and how that's possible when we talk about momentum. And the first thing we're going to do is the momentum equation that you used in the lab report you submitted on Tuesday. We're going to go through the derivation of that a little bit. And I don't often focus on derivation of the formulas that we use, not from first principles, just because I remember being a student and not really caring that much, and it didn't usually mean a lot to me. But in this case, I think it's important because the origin of the momentum equation is very similar to how we actually use it, and maybe it does inform certain sign conventions that's important for us to remember. Speaking of sign convention, you remember in Euler's equation, that was another one where it was very important for us to keep track of what was location 1, what was location 2, and you got the wrong answer if you messed up the sign convention. And that's not a minor mistake, that's a major mistake. The same thing's going to be true even more so when it comes to momentum. You're going to have to be a little bit meticulous and not just start jamming velocities in willy-nilly all over the equation, because you have to be kind of careful that, that you get the velocity direction, and in versus out. So with that preview, if we start off with Newton's second law, and substitute our definition of local acceleration, meaning a change in velocity with respect to time. And we've talked about several different kinds of acceleration since the first exam. We've talked about centripetal acceleration. We've talked about convective acceleration, where convective acceleration is what causes a change in velocity with respect to position. But here, the local acceleration is the standard acceleration that you remember from high school physics, a change in velocity with respect to time. Now, we're going to say with the Reynolds transport theorem, when we defined this idea of a system of particles, not just one solid object like you sometimes do in standard physics problems. You know, you've got a car that's accelerating or something like that. We'll set that aside and think about a system of particles where it's a mass of continually connected fluid particles that are not necessarily in the same place. You know, they can move over time, their shape can change over time, the direction can change over time, but it's just some particles that have mass and connected. And so a fluid jet, for example, is an illustration of what we might consider a system of particles. A fluid jet that's being pumped from a tank in a bench, maybe. So if we substitute in Reynolds transport theorem and say that we are going to keep track of accumulation inside of the control volume of momentum and flow of momentum through the control surfaces. That's what we, with the widest view, hope to achieve. The truth is that it's very rare for momentum to be accumulated inside of a control volume. It's not impossible. You can accumulate momentum. And an example of accumulating momentum would be, if you remember back to the freshman class when we had those wind turbines. Remember you built the blades for the wind turbines? Well, once it's spinning, if you start to spin it and then there's no wind, it'll slowly, gradually slow down and come to a stop. But when you just first push that blade and it's spinning, it has accumulated momentum at that point. So momentum accumulation will be rare with the problems that we solve, but you can envision a physical system that has momentum accumulation. Like if you get some sort of a flywheel spinning, then that momentum is there to be harnessed later when you need it. But if we combine this idea of forces being the result of an unbalanced acceleration, remember that this came from acceleration and mass. If we combine that with Reynolds transport theorem, what Reynolds transport theorem says is that there's some force required to hold the system steady. That's how to interpret the left side of that equation. If you're going to write it out, I'm going to emphasize this a lot of times during today's lecture and the coming 2 lectures for next week, is the force required to hold the system steady. In the lab, the system you were holding steady was the deflector plate. You were playing around with the velocity of the jet to try and get it back into equilibrium. How did you know it was in equilibrium in the lab? Do you remember what visual cue told you the system was back in equilibrium? It was the needle and that silver ring that was around the plate. And so you were fine-tuning the velocity until you saw that the system was back in balance. You had loaded weights on the top, and for some of those deflector plates, you were putting a lot of weight on there, weren't you? I mean, all the weight that there was. And you still had plenty of additional velocity you could have given it. So those weights that you added were representing the force required to hold the system steady. So that's what the first sign convention hint I want to give you is, we're going to sometimes have questions that ask, what force is a jet imparting to the system? And that will be like the equal and opposite of what the equation actually calculates. The equation calculates how much external force is required to hold a system steady when the system is being impacted by a jet. But sometimes the word problems get a little tricky, and they'll be saying, well, not what force is the jet adding to, not what force is the plate deflecting on the jet, but vice versa. And we'll get to that with a physical example in a minute. Force required to hold the system steady is equal to the accumulation of momentum in the control volume and the net flow of momentum in and out of the control surfaces. Momentum can come in, momentum can come out. And in the lab, what you saw was a jet of water, and let's take as an example the 30-degree deflector. It had the water spraying out like this. So control surface, control volume, that's really abstract until you start drawing them. Our control area, the part that we're interested in, is boxed in red there on the screen. And so we have, since there's a jet of water going this way, there's the momentum in. And since the jet of water comes out at an angle, now there's not just two. You remember that it was actually a cone, right? But when I do a cross-section of a cone, it looks like there's two different jets there. So don't get confused and say, well, I have to have 2 times velocity or 2 times the mass flow rate. There's just one stream going out, but it's got a strange shape. So this equation is saying, what force is required to hold the system steady when you've got a mass flow rate coming in, a mass flow rate going out, and the simplifying assumption we made in that lab is that the velocities are the same. And that's probably the biggest error as far as assumptions go that we made. And when I looked through your labs, I was looking to see if you mentioned that assumption. I had pointed it out that it's not a realistic thing that a jet that's going up and then is getting in contact with a surface that has friction, it's not going to be going exactly the same speed, but we don't know how much it slows down, so we assumed that it is the same speed. So that was an assumption that we made out of necessity, but it's not altogether true. So this is the kind of thing that we're going to use momentum to try and solve, and lots of other applications, not just this one limited case. Usually, we'll have problems where there's no accumulation of momentum. Inside the control volume here, for example, there's no propeller or flywheel spinning around trying to accumulate the momentum. And so we'll usually neglect the momentum accumulation term from the Reynolds transport theorem side of the equation. Now this is different from the Reynolds transport theorem as we've seen it before, because you'll notice that there's a velocity term in here. When we were doing just mass, in chapter 5, continuity equation, when I first introduced Reynolds transport theorem, what it was change in volume, V times the differential area. But now we've got a density term and a velocity term. And that means that there's a mass-related property that Reynolds transport theorem is used to solve problems on. And the mass-related property here is momentum. Momentum is a function of how much mass is in the system. So that's how we are able to use Reynolds transport theorem, is by adding an additional term to each. So if we cancel out this accumulation term and we just have the transport component, which is the flow in and out of the control surfaces, this is the momentum equation that we're going to transform in kind of like the functional version that has all of the sign convention notations, in versus out. Velocity is positive to the right, velocity is positive up, and so on. A word about forces. There's different kinds of forces, and the force that we're talking about when we say the force required to hold the system steady, that is not a body force. There are forces that can act without contact, like electrostatic forces, magnetic forces, gravitational, but we're talking about a surface force when we're doing momentum problems. It requires a physical contact, and so what is causing this force to be needed is the fact that the jet comes into physical contact with that deflector plate. And we don't have to, because this is vertical, we don't have to separately account for gravity. The momentum equation already accounts for gravity. So it's not going to be a secondary consideration that we have to keep track of. So here it is. I should say, ta-da, there it is. This is the functional version of the momentum equation in the x direction. You know, if your problem is dealing with vertical forces and vertical momentum, then you just change y. Any place it says x, there it is. Y has been substituted. Anybody remember what the m dot symbol means? I bet all of you do. Mass flow rate, right. Mass flow rate. What units does it have? Mass per time, so it would be kilograms per second. When we solve problems, that's what we'll express it in, kilograms per second. You know, in a problem statement, just to make it hard, I'll maybe say grams per hour or something like that. But that's just to give you a chance to make the conversion. All right, so mass flow rate. Now we've got O and I. Anyone want to venture a guess? O and I, what that means? Out and in. Okay, so here's the in, the mass flow in, here's the mass flow out. The weird thing is if you look at it, it's the out minus the in. And that's one of the things that I always have to remind myself, because it just, I don't know why, but it seems natural that you'd say in minus out. Maybe it's because I'm so used to saying accumulation is in minus out. I guess it's probably because I'm always thinking in these terms that I always have to force myself, oh no wait, we have to do the mass flow out and then minus the mass flow in. So, you know, if I sometimes tell you about the most popular mistakes that students will make in a quiz or an exam. Accidentally switching out and in is a really popular mistake. When students are working on the exam and thinking, which mistakes do I want to make today? The one that they choose to make most often is in minus out. The other thing that's hard is that velocity here has a sign convention associated with it. And so to the right is positive and up is positive. And this is the same convention we had with Euler's equation. Mass flow rate's a scalar, which means it never is going to be negative. Mass flow rate, you can't have like -3 kilograms per second. Unless, I don't know, maybe if you've got a jet of water going into a black hole, maybe that would be a negative mass flow rate. But in these problems, we're always going to have positive mass flow rates, even if, let me show you what's still going to be a positive mass flow rate. If we had a jet of water going this way, and we know the velocity is 10 meters per second, but because it's to the left, we'd call it -10 meters per second. And let's say that we know it's a jet of water with a cross-sectional area of 1 square meter. And it's water, so it's 1,000 kilograms per cubic meter. Mass flow rate, the formula for it is density times volumetric flow rate, which is density, area, times velocity. So because we're in the habit of keeping track of velocity for the v term, sometimes people get in the habit of also putting the negative sign in the velocity here. And so it's an easy mistake to make to say, I've got 1,000 kilograms per second. I've got an area of 1 square meter. And my velocity is -10 meters per second. So therefore, I've got 10,000, -10,000, what am I doing here? Mass flow rate, kilograms per second. So that's my mass flow rate is -10,000. Now that's not true. Mass flow rate is a scalar, so it's always going to be positive, even if the stream itself has a negative velocity. Everybody get that difference? Everybody on board? You only account for the negative sign of the velocity one time in the v term itself. Mass flow rate's always positive. So here's an illustration. If you've got a rectangular control surface, in is the stream that goes into the control surface, and what we're going to call out is the stream that goes out of the control surface. So here's the, positive x versus negative x, positive y versus negative y, and then we also have to be careful to distinguish between the in streams and the out streams. So let's put that to the test. It's going to seem ridiculously simple at first, but then after a couple of these, it actually gets kind of complicated when there's multiple streams and it's going to the left. It'll require some diligence and attention. So here we've got the velocity out is positive, velocity in is positive. So if we were substituting it in to the equation on the screen here, whatever the velocity of this out stream is what we'd substitute there. And whatever the velocity of the in stream is, we'd substitute here. They're both positive. Okay? Here we've got two different in streams. And what you'll remember about the momentum equation is it says the sum of the forces required to hold the system steady is equal to the sum of the mass flow rate out, velocity out. If this is x, for example, then it would be velocity out in x. And minus the sum of the mass flow rates in, velocity in x. So there's more than one stream in the x direction here. So we have to account for both of them in the momentum equation. So in stream 1 is in positive direction. Stream 2 is negative. So whatever velocity it has, when we get to this term, is going to have to be a negative value in that velocity term. Out, that is negative out. Okay, so here I haven't labeled them. What I'd like you to do is in the margins, label the streams in the same way that I have. So stream 1 has both an x component and a y component. In which direction, is it positive x or is it negative x? Stream 1. Is stream 1 positive y or negative y? Classify them. Stream 2. Classify its x and y components. And same with stream 3. I'll give you just a minute to think that through. Remember if I've got those. All right, we'll go through it. So stream 1. Let's see. The velocity in x for stream 1 is positive, and the velocity in y for 1 is negative because it's down. Okay, stream 2. The velocity in x is negative because it's to the left, and the velocity component in the y direction is also negative. In stream 3, the velocity in the x component is positive, and the velocity in the y direction is also positive. All right, not too bad. Now here's how you solve problems like these. You'll hopefully have a picture to begin with, or from the word problem that you're solving, we'll come up with your sketch. These problems really are helpful if you have a sketch. So I'd encourage you to do a drawing if they don't give you one. And then once you have the system drawn, put in the control volume enclosing where the action is happening. And like, how do you know where the action is? Well, the action is when the jet is impacting something. If it's a tank of water and there's a fluid jet coming into the tank of water, well, you should be sure that your control volume encloses all of the water that's being impacted, and the control surface crosses the jet that's coming in. So identify governing equations is talking about the fact that sometimes we'll have combination problems where you'll have not only a momentum problem, but you'll also have a Bernoulli's problem in the same combination. It's going to be kind of like in Chapter 5 where we had continuity and also Bernoulli's in the same problem. Drawing the forces like I've done here, you sketch the forces where the jet is in contact with the deflector plate, the added weights that are coming down from above, verify that there's no momentum accumulation in the problem, and then sketch the momentum flow vectors. And so the vectors would be, here's the velocity in, and it has a certain mass flow rate in. Here's the velocity coming out, and it has a certain mass flow rate out. All right. So thinking about the jet again, chemistry. Do you feel a little anxious when you see a chemical equation on the screen there? Sometimes. I liked chemistry when I was an undergraduate student, but then when I got to graduate school, I developed a proper hate for chemistry. So here's the formula for kerosene, and kerosene's burned in the presence of oxygen, produces carbon dioxide and water. So the reason I bring it up is because we know the fuel burn rate, and we know how much thrust is generated per boot. So I want to use all of this information to find out what's the minimum exit gas velocity that could generate that much thrust. We had the boot. Let me do a little sketch of that boot and what it looked like. Conceptually, it's just a black box where stuff goes into the black box and stuff goes out of the black box. I drew it like this. Air goes in, and so does gas through those little tubes, and then what comes out is the jet itself. The air consists of O2 and other gases. And the gas itself, what I mean is the kerosene. Okay. The ratio of fuel to oxygen, if we have 2C12H26 plus 37O2, you remember from the periodic table, you can look up molecular weights, right? Molecular weight of oxygen is 16. Molecular weight of carbon is 12. Hydrogen is 1. Everybody knows hydrogen. So if you multiply the number of carbon atoms by the molecular weight, the hydrogen by the molecular weight, the kerosene is 340 grams per mole. And the oxygen is, for 37 oxygens, 1184 grams per mole. So what that tells us is that there's a ratio of 1 to 3.482. And that's grams of kerosene to grams of oxygen. You've heard of fuel-to-air ratio before, right? Like back when people had cars with carburetors, they had to always tune up the car by adjusting the fuel-to-air ratio. Now that there's fuel injectors, that's kind of done computerized, electronically, automatically. You don't have to manually make that adjustment. But the reason we want to know that is we're going to find out how much air is passing through that engine. If he's burning fuel at a rate of 0.5 liters per minute, that can give us a clue about how fast the exit gases are coming out. So what is 0.5 liters per minute? 0.5 liters per minute is 500 cubic centimeters per minute, and the density of kerosene is 0.795 grams per cubic centimeter. That means that 397.5 grams per minute are being burned of that kerosene fuel. In terms of the mass flow rate, that is 0.006625 kilograms per second of kerosene. So how much oxygen is going to be used? Well, we go to the kerosene to oxygen ratio to know that. So oxygen is 0.02307 kilograms per second. So that's the mass flow rate that's going into our control volume. Remember, we said that there's gas going in and there's oxygen going in. Other gases are going in as well besides oxygen. Our atmosphere that we breathe is only about 20% oxygen. The vast majority of the rest is nitrogen, and then there are also other trace gases like hydrogen, helium, carbon dioxide. Let me move over here. Let's take a look at when it says 16 kilograms of thrust, what that means. It means that we have, if we multiply the mass times gravity, 16 kilograms of thrust times 9.81 meters per second squared, there is 157.0 newtons of thrust per boot that's being developed. Air, like I said, air is only about 20% of 20% oxygen. So we have to find out, if this is how much oxygen is going into the boot, how much air is entering the boot. And so air mass flow rate is going to be the oxygen mass flow rate divided by the fraction of air that is oxygen. So the oxygen mass flow rate was this 0.02307 kilograms per second, and 0.21, that's the fraction of air that's oxygen. 0.1099 kilograms of air per second. That's the air flow rate. How much is going through the boot. So now we can jump into momentum. We've done the chemistry. Here's what momentum has to say. Momentum says sum of the forces in the x direction are equal to the sum of the mass flow rate out times the velocity out in x minus the mass flow rate in the velocity in x. Let's find out what's going on. Remember when he was sitting in the back of that trailer? We'll assume that the air, the velocity in is 0. basically, if we draw our control volume like this, the air is stationary before it gets sucked into the jet. So the incoming air has a velocity of 0. Once he starts flying horizontal, then that's not true anymore. You know, with forward movement, then he's actually going to be developing less thrust. You get the most thrust right at the beginning when the incoming air is not yet moving. For velocity n is 0 at the beginning of the jump, and the total mass flow rate in is going to be the 0.1099 kilograms per second, which was the air, and then also the kerosene, which was 0.006625 kilograms per second. So the total mass flow rate is 0.1165 kilograms per second. So let's put that in here. What forces are there and so on. We know the mass flow rate. What we don't know is the exit velocity. Like how fast does that exiting exhaust gas have to be moving? So if we have the velocity in is 0, this term goes away. So we're going to have force is mass flow rate out, velocity out. And what we want to know is the velocity out, and we're going to do force divided by mass flow rate out. So the force was 157 newtons divided by this combined mass flow rate of 0.1165 kilograms per second. That means that the velocity of the gases coming out are 1348 meters per second. That's the exit velocity required to generate that thrust. Has anybody ever launched rockets before? You know, the model rockets made by a company called Estes, maybe when you were a kid. Those little rockets are kind of like this. Those little rocket motors have, here's the fuel inside of the rocket motor, and then it sort of ends. And then there's a curved segment like this. And you put a little igniter in here, and it starts the rocket fuel, and the rocket fuel starts going out this way. But those little engines that you buy in the hobby shop, you can actually get them at Hobby Lobby, these little rocket kits. The different engines generate different thrusts, and they have some that are called like A, B, C. That's how they rate them, A, B, C. And when you first buy a rocket, you're supposed to go and get an A thruster, because they don't push very hard. It'll just maybe go 100 feet or something, and then you verify that the fins aren't going to fall off and you didn't burn yourself. You basically learn the procedure, and then you switch to one of these other rocket motors. Well, they all have about the same amount of rocket fuel in them, but the way that the B and the C are able to lift the rocket higher is by changing the diameter of the exit. So a C would maybe be a really small diameter, like this. It would have just a little bit of area that those gases can exit out of, because if you have a really small area, then the velocity is going to be big. And so you've got a big exit velocity, it generates more thrust. That's kind of what's going on over here is, in order to generate that much thrust, 16 kilograms of thrust per boot, you've got to have a really high velocity because the mass flow rate's so low. And it's got to be one of two things to generate force. If you want to generate a lot of force, you either have to have a big mass flow rate or a big velocity. Here, it's a low mass flow rate. He doesn't have a lot of mass that he can put through the boot. because there's just those two bladders of fuel, and so if you don't have a lot of mass flow rate, then the key to generating thrust is a high exit velocity. So that's what we went through. I don't know why I got so fascinated with these jet boots when I saw them, but I wanted to do all the calculations from beginning to end, and so I thought I'd make you suffer through them as well, including the chemistry. All right? We won't do too many formulas this semester, but there you have it. Is that the only thing that's in the notes for today? Gee, I don't know. It goes against my principles letting you out this early, but... Oh, okay, well, at least you're suffering at some point today. All right, even if it's not me, the fact that you're suffering will make me... Yeah?
Are we going to need to know any of the chemistry for tests?
No. All right, have a great day. I'll see you Tuesday of the week after next. We'll have an exam. But you'll hear my voice through the recorded lectures, and you'll send me emails if you've got questions along the way.